going to look at some alternative ways of finding the vertex and things like that. So, same example as yesterday, sketch the parabola. I'm not going to actually redraw it, but say we had that question, sketch the parabola. So there is y equals x squared plus 8x plus 12. If we make use of the idea of completing the square, we can get the vertex very quickly. Don't worry about the number 12. We're interested into the x squared plus 8x part. If I was to complete the square on x squared plus 8x, of course it would be half the coefficient of x. So I'd end up with x plus 4 all squared. But of course x plus 4 all squared would give me 16, not 12, so I need to subtract 4. Now if we go back to the ideas when we looked at curve sketching about shifting curves, we can read from that straight away where we've shifted the vertex to. So we know the vertex must be at the point -4, -4. So that can sometimes be quicker than finding the axis of symmetry, then substituting in and getting the y value. So it's an alternative way of doing that. Now, if I wanted to find the x-intercepts, well, yes, I could go back to the original one and factorise that. But if I've completed the square, I suppose I could make use of that and say, well, all right, when's that equal to 0? So when's x plus 4 squared equal to 4? So x will be -4 plus or minus 2, and we get the x-intercepts. Don't know necessarily that I'd do it that way or not, but it's an alternative. What about if we had that question from yesterday? Write down the quadratic, roots 2 and 8, vertex 5, 3. If I say, well, hang on, I know that because it's been shifted to 5, 3, then it must be in this form. X minus 5 all squared plus 3, but it could be some multiple of that. But notice I only put the k in front of the x minus 5 all squared. Because if I multiply the 3 by k as well, it means my shift up is not going to be 3, it would be 3k. So the 3 is by itself, the shift up is by itself, the constant is only times the x minus 5 squared. So alright, I've made use of the vertex, then I could pick, well I guess I could pick either one, 2 or 8. Which one did I use? I used 2, substitute that in to work out what k would be. Play around with that, and you may remember from yesterday our answer was k equals -1/3. So there is our equation. If I expanded that all out, yes, I get the same as yesterday. Okay, so that's making use of the idea of completing the square. Another idea is using the discriminants. Now, the discriminant is that bit under the square root sign in the quadratic formula, so b squared minus 4ac. Symbol we often have for it is a delta, a capital delta. So b squared minus 4ac. The vertex, well, we know the axis of symmetry is minus b on 2a. But what you might not have known is the y value of the vertex turns out to be minus the discriminant on 4a. It'll always be that. And of course, well, if we wanted to find the zeros, all I've really written down there is the quadratic formula, but I've used delta instead of writing b squared minus 4ac. Now, if that discriminant is less than 0, that tells us something about our parabola. It means we're not going to have any x-intercepts. Because if you think about it, we're finding the square root of a number that's negative, which of course, no solutions. So sometimes, and we'll look at this idea again a little bit later, but that can be a useful thing. Rather than physically going and solving the whole quadratic, we can just look at the discriminant and realise, oh, hang on, this one won't solve because the discriminant's negative. If it was equal to 0, then it would just touch the x-axis because it's only going to have one solution. And of course, if it's greater than 0, then I know it's got 2 possible solutions. So that's another thing the discriminant can be useful for. Okay, back to our example again. Sketch the parabola. Well, if I now use the discriminant idea, the discriminant for this one, b squared minus 4ac, turns out to be 16. So my vertex minus b on 2a minus the discriminant on 4a. And sure enough, we get our minus 4 minus 4. That's our first bit of theory for today.